Welcome to our discussion on linear functions and models. Here are the objectives for this video. Let's start off by discussing linear functions. A linear function is basically a function that takes on the form y equals mx plus b, right? Only when we talk about functions, instead of y, we use f of x, and instead of m for slope, we're just going to call it a, but it's the same darn thing, right? A is your slope, b is your intercept. You already know what a straight line is, so you know what a linear function is. Here are some examples of some functions, and we're going to try and determine if they're linear or not, and if they are, we're going to express them in the ax plus b form. So let's start with the first two. We can see that very easily all we have to do is swap places with the 2 and the 3x, and we get ax plus b, right? For the next one, we have to actually do the distribution, right? Multiply through by 3, then move things around, and we get negative 6x plus 3. And of course, a is negative 6, b is 3. So both of those are linear. Then we move on to c. Again, we have to do the distribution, and we're left with 4x plus 3x squared. And we recognize that can't be linear because we have that x squared term. And obviously, linear functions can't have any powers of x. So we know it's not a linear function. And of course, that's a quadratic, right? That ends up being a parabolic function of some sort. The last one, we go ahead and do the division this time, and we get 1/4 minus 5/4 x, and then again, rearrange the terms to get it in the ax plus b format, with your slope being negative 5/4 and your b being 1/4. Okay, simple, easy stuff. You guys have dealt with straight lines before. What about slope and rate of change? Well, as you've seen from my other videos, slope and rate of change are the same darn thing, right? Rate of change is just the slope of a straight line between 2 points on a function. If it's a curvy function, fine, but if it's a linear function, it's just the slope of that function, right? Because any 2 points on a straight line are going to have the same slope. So this is just a kind of a formalized argument of what you already know, right? That slope is change in y over change in x, and since the y's are the same things as f of x's, right? You get f of x2 minus f of x1 over x2 minus x1, and you go, hey, that reminds me of that average rate of change formula that I saw before that was f of b minus f of a all over b minus a, and I go, yep, told you, same thing. All right, so since we know that the average rate of change of a linear function is the same for any 2 points on that line, it's simply just called the rate of change, right? Because the average never changes, it's just the rate of change. So the slope of the linear function becomes just the rate of change of that linear function. Okay, here's an example where we can use this simple function that is supposed to represent the water level at some time t in a reservoir. We can sketch the graph, we can find the slope of the graph, and then we can figure out at what rate is the water level changing, i.e., its slope. So here's the graph of the function. We do that very simply by just plotting 2 points, because you only need 2 points to create a straight line. From those 2 points, we can also find the slope, and it's a slope of 4.5, but we also knew that just from looking at the function, right? 4.5t, that's my m, so it's a slope of 4.5. Since time is measured in years and the water level is measured in feet, the water level in the reservoir is changing at a rate of 4.5 feet per year, right? So we already knew it was a rate of 4.5. All we had to do was add in the units of measure, right? So instead of just 4.5, we can say 4.5 feet per year. And since it's a positive, we know that the water level is going up. All right, what about using linear models? Well, linear models is really just a fancy way of saying, hey, we've now got a linear function. And instead of it being some arbitrary linear function, this linear function is actually going to model something in the real world, kind of like that reservoir question we already just saw. So you've already dealt with linear models and didn't even know it. Right? It's just it's another type of function. It's just a function instead of being something that was made up. It's supposed to model something in the real world. So here's a typical example, right? The relationship between two quantities. So in this example, we've got gallons and time. So the graph gives the amount of gas in a tank that's being filled. So how fast the level of gas is filling over time as you're filling up a tank. And then this next is showing how fast it's being drained. And again, you can calculate the slope and see that it's being drained at a rate of 0.03 gallons per minute. Maybe there's a hole in it, or maybe it's just because it's attached to an engine and an engine is running and it's draining out the fuel because it's burning it off to run the engine, right? Another simple example would be water being pumped into a swimming pool at a rate of 5 gallons per minute. And if the pool initially contains 200 gallons of water, we can now show a function to show us how fast the volume of water is increasing, how long it will take until it's full, right? Because the pool has a capacity of 600 gallons. All these things can be modeled by a linear function. So here's our typical linear function. We're going to call it v of t because it's a volume function now. You could have just called it f of x, right? I mean, it's the same thing as f of x. We just like to give our functions labels that make sense. F of x is just an arbitrary, any old function. But because this is modeling volume over time, we're going to call it the v function for volume, and we're going to use t instead of x for time, right? So it's nothing different than f of x. We're just giving it kind of a more obvious name. Now, we were told the rate of change in volume was 5 gallons per minute. So rate of change, remember, is slope, so that means A is equal to 5. And since the pool started with 200 gallons when we started filling it, that's what happens at time 0. And time 0 is our intercept, that's our B. So we now have the function, the volume function is 5t plus 200. We can use that function to figure out how long it's going to take to fill the pool, because remember the pool has a capacity of 600 gallons. So all we have to do is plug in 600 for volume, right, for the V part. Solve for t. You subtract the 200, gives you 400. 400 divided by 5, 80. It's going to take you 80 minutes to fill your pool, right? So that's just a simple example of how we can use a linear function to model something in the real world. And that's everything we need to know.